Nitration of benzene involves adding a nitro group, NO2, and it takes place via the following conditions: is you have to add nitric acid, sulfuric acid, and heat. So it's a very, you have to be very cautious when you do this reaction because it can be very, very dangerous. And you would get a nitro group right there. So the electrophile is made by adding the nitric acid and sulfuric acid, and that electrophile is called a nitronium ion. So let's look at the step one. So for step one, you have your nitric acid. Let's draw out the Lewis structure. And of course, you have sulfuric acid. So nitric acid is not as acidic as sulfuric acid. So we can say that this is less acidic. And this is more acidic. So what happens is that the lone pair on the oxygen with the hydrogen in the nitric acid is going to attack and deprotonate the H on sulfuric acid. And of course, this is going to give you the following. So you're made water right here. Now, you know from organic 1 is that this is a weak, it's a leaving group. It's a weak base, so it's a leaving group. It's actually a good leaving group. Let's put this here. So it's going to be kicked out. Let me just for more space here because we have enough. We will make then the following. Electrophile plus water. Now we're going to need water for the step 3, or we can use the conjugate base of sulfuric acid for the deprotonation. Very good. So this right here is your electrophile, and that's called the nitronium ion. So once again, here's our benzene. And we can just draw nitronium ion just like this. There's a positive. So then your benzene ring is going to attack the nitronium. Once again, here's our NO2. We're just going to include it like that. And here's our H, and there's the positive charge right there. So you have now, of course, 3 resonance structures. So you should pause and you should draw them. Very well. So you know again, this is a resonance stabilized carbocation. And of course, now the next step, and by the way, before we actually move on, I want to say is that the first step is always your rate limiting step. Oops, not this one. I meant the first step in the attack. This is your rate limiting. Slowest step. Simply because you're disrupting aromaticity. So you should be able to make a prediction that the next step, would it be faster to regenerate an aromatic ring? And the answer is, what do you think? The answer is yes. If you said yes, great. You're now learning exactly what should happen and why it should happen. So again, we will take the very first structure here. And there's a positive. And you have 2 choices. You can either use the conjugate acid of sulfuric acid, bisulfate, or water to deprotonate. It doesn't really matter. So I'm just going to use water. Or your book may use we usually just list it like that. Or again, you draw it from the negative to that H right there. It's actually one of the oxygens. So in this case, your product then is the nitrobenzene plus H3O plus HSO4 minus, which is your acid component. Very well, that's the product right here. In the next reaction, we're going to have sulfonation. And now you can see that we're adding an SO3 group. So we make then benzene sulfonic acid. This reaction is also requires harsh conditions. If you notice here, we have a very acidic it's sulfuric acid. So let's actually go ahead and talk about the mechanism for that. So The outcome of this reaction is the following. You can do it at room temperature with sulfuric acid, or you can do it with fuming sulfuric acid, where you have the sulfur trioxide in the presence of sulfuric acid. Very dangerous material, obviously. So let's actually begin with the mechanism. So what you have here is two molecules of sulfuric acid. I'm only going to draw one of them, and the other one can just simply be shortened this way to be brief. It's basically the same structure as that, but we only show the part that involves the reaction. So again, what's going to happen is these lone pairs are going to attack the H proton, deprotonate the other sulfuric acid molecule, yielding the protonated sulfuric acid. Once again, we have a good leaving group, water. So then it's going to leave. That's what a leaving group is, or that's what it does. And you will be making now your electrophile. Let's put the right there. Of course, it has the trigonal planar geometry that would look like this. So once again, the last step is same as we've seen before. The second and the third steps is the attack by the benzene. We're just going to shorten this as SO3H. And there's our H right there. Once again, I'm not showing you the other resonance structures, but you should be able to draw them. They're not going to be different than the ones we drew before. So plus here, I'm going to write on the top here, plus 2 resonance structures. So what's left is you either once again have the water molecule or the bisulfate attack. So in this case, we can have the water molecule. Pardon my drawings here. And that's going to fall right there. And then you will restore aromaticity. Very well. In the next two reactions, we will talk about Friedel-Crafts alkylation and Friedel-Crafts acylation, two other important reactions.